In this video, I'll be showing you how to use a clamp-on multimeter. I'll be explaining what all the different selections are and how to use them. I'll try to explain this in a simple and down-to-earth way, but the meter that I'm going to be using is loaded with a ton of different features that some other meters don't have. So for those of you that are interested, I will be going over some of the advanced features just briefly so you'll know what all of them do. To start things off, let's begin with voltage, which is represented by this letter V right over here. There's two types of voltages. There's direct current and alternating current. On some meters, they're going to be separated. There's going to be one for direct current and one for alternating current. But on this meter, they're both under one selection. And to change between the two, I would press this select button, which brings me to direct current. This symbol right over here, it's one solid line and dashed lines right under it. And if I press select again, it switches me back to alternating current, which is this wave symbol right here. In order to test voltages with our meter, we are going to need to plug in our meter leads. And those go in right on the bottom over here. The red one will go to the plus sign, and the black is going to go to COM. In order to test any kind of batteries, we would use direct current, and to check anything that comes from the energy company, we would use alternating current. So outlets, light switches, anything that comes from the breaker panel, all of that is going to be alternating current. So let's test some batteries and see what this would look like. So I'm going to switch to DC current, and then I got a round battery right here, a round 3-volt battery. And we got 3.2 volts. Perfect. That means this battery is good. Here's a C battery, which is 1.5 volts. It's reading 1.59. So this battery is good as well. And here's my little drill that uses a 12-volt battery. The slots on this battery are really thin, so I can't actually fit my meter leads in here. So my options are either to stick a wire in here or some kind of a paper clip and then test it with the paper clip instead. Or if your meter came with these thin meter lead attachments, they work really nice in narrow spaces like that. So with these two attachments, I should be able to get in there and check my battery. And we are reading 12.32 volts. And by the way, if I flip the leads, on most batteries, it doesn't matter which lead goes on which side, you're still going to get the same read. Most batteries are labeled though, so you want to put the red lead on the plus and the black lead on the minus. And we're getting 18.2 volts. So this battery is good. If this battery was bad, we would get a reading that is really low, or it would read OL on the meter. This car battery is 12 volts, and with a meter, we can verify that it's good. And when testing alternating current, do exercise caution because live electricity could be dangerous. Don't touch any exposed metal or exposed wires. When testing alternating current, it's a lot safer to use one hand only. And what helps with that is if your meter has a little holder like this, you can plug one lead in to the holder and use your meter as one hand and use your lead as the other. Testing AC voltage is a perfect way to see if something is getting power or not. It can be used to test furnaces, air conditioners, household appliances, circuit breakers, thermostats, and etc. Some meters will also have a low Z voltage setting. Low Z stands for low impedance and is used to eliminate ghost voltage. When I have my meter set to voltage, it is a lot more sensitive than the low Z setting. It catches any kind of fluctuations in voltage. For example, even if I start wiggling my leads, look at that. Even just wiggling my leads gives me a little bit of a ghost reading. So if you're checking an outlet or any kind of power wires, the ghost voltage could be a lot higher than that. But if I switch my meter to low Z, it becomes less sensitive to those fluctuations, and it's not going to pick up any kind of ghost voltage. Another cool feature about the low Z setting is that it has automatic mode, which switches automatically between DC voltage and AC voltage. When you plug your meters in, whether you're testing a battery or alternating current into an outlet, it will automatically determine what it is you're testing and give you a read. But if you don't like that, you could always press the select button and go to either alternating current, low Z, or direct current, low Z. Next up, we have the omega symbol, which stands for resistance. This setting is used to check electrical loads, such as motors, compressors, resistors, or anything that requires electricity to turn on. When you're testing resistance and you're getting a reading that says OL, that usually means that that component is bad. And here's an example of a really low resistance reading. If I touched my 2 meter leads together, there is 0.1 ohms of resistance, which is basically almost no resistance at all, and that's because my leads are literally touching each other. There's no resistance between them. The meter that I'm using is auto ranging, but when I let go of my leads, if you look at the symbol right here, notice how a K appears and an M appears. That stands for kilo and mega. My meter automatically ranges and it selects the proper range that I need whenever I put my leads on something to check resistance, but some of the cheaper meters, you have to select that range yourself. If I measure this light bulb over here, which I know is bad, my meter is either going to read over limit or the reading is going to be massive, which also means the light bulb is bad. So what I'm getting right now on my meter is 12 million ohms. Usual light bulbs go up to like 100 ohms, so we know that this bulb is for sure bad. And if I was using a manual meter, the way I would check this is by putting the meter leads on, and then I would set the meter to the highest ohm reading and start going down from there. On most meters, if the number 1 appears on your display, that means you took it one step too far. Just back up by 1 click and you should get the proper reading. The easiest way to select voltages would be done in the same way. Here's a water heater element, and we can use resistance to check if this element is good or not. If an element is good, the resistance on it is usually somewhere between 10 to 20 ohms. So if I put my meter leads on both screws on the element, we are getting 12.6. So this element is good. But if you had your leads on there and you were seeing OL, that means that element would be bad. Auto-ranging meters will automatically select the proper range for you, but it does allow you to manually switch the range if you want to do so. All I have to do is just press this range button, and it'll switch from ohms to kilo ohms, and then higher, higher, mega ohms, even higher, and back to ohms. Also, one very important thing to remember when you have your meter set to this resistance setting right here is that the power has to be off to whatever you're checking. Power off, and usually the wires have to be disconnected before you check resistance on anything. For example, if we take this light switch right here, usually there would be wires going to it. If you wanted to check the resistance of this light switch, you have to take the wires off before you check the resistance, and the power has to be off. If the power is off but the wires are still on, you're going to get a false reading because you're also reading the wires along with the switch. So let's try checking the resistance of this light switch. Right now it's in the off position. If I put my meter leads on either end, we see that I'm getting a read of OL. When you see OL, that means that there is no connection between these 2 points inside of here. So for example, if you were checking a motor winding and you're going to be seeing OL like that, that means that winding inside of that motor is probably burnt out and there's a break inside of that winding. But if I turn the switch on, we see that now I am picking up some resistance. It's very small because it's literally like a little piece of metal inside of the switch, so there's not much resistance to the electricity. Whereas a motor winding would be resisting the flow of electricity a lot more, so the reading would be higher. Another really useful feature is continuity, which is this symbol right over here. Checking continuity is similar to resistance, but the meter is also going to beep if there's a connection between the 2 points. So if I put my meter leads on here, we're not hearing anything. That's because the switch is open. But if I close this switch, put it in the on position, now we're hearing a beep. Continuity is perfect to check any kind of switches. including the safety switches in appliances and HVAC units. Fuses are also easy to check in this manner. When you're checking for continuity, you're literally checking if there's a connection between point A and point B. For example, see how this metal piece is all just one piece? That means there should be continuity between these 2 points. And there is. And there's continuity there too. And of course, this only works with metals, which conducts electricity. Any kind of material that does not conduct electricity well, like plastics or rubber, those are insulators. And of course, we're not going to be picking up any kind of continuity when we're checking plastic. The continuity setting is also a great way to check to make sure that your meter leads are good and there's no breaks in the wires. If you just touch the 2 leads together, you should get a beep. If it's not beeping, then you know that the wire is broken on one of the leads. Next up, we have the capacitance setting, which is used to test all kinds of capacitors. Capacitors are measured in farads, abbreviated by this letter F right over here, and the letter N right in front of it stands for nano. The letter N is rarely used because it's such a tiny reading. Usually what you're going to see is a UF, which stands for microfarads. Just to show you what I mean, 0.1 microfarads equals 100 nanofarads. Just like the resistance, this meter automatically selects the proper range, but I could select it manually if I so wanted to. So there's the nanos. If I just click on that a few times, that brings me to the microfarads. And if I click on it again, it moves the decimal point by 1 place. And one more time, moves it once more. I prefer to just leave it on auto and let the meter select the proper range. So right here I have a dual capacitor, which is rated 45 microfarads and 5 microfarads. And sometimes instead of this backwards letter U, you're going to have the letter M. So it'll be MFD, which is the same exact thing as UF and stands for microfarad. This right here is a dual capacitor, which means there's 2 capacitors in one. So let's go ahead and check both of them. Let's start with the larger reading first, which is supposed to be 45. I am getting 43 microfarads, which is pretty good. I believe this one is still in range because it's plus or minus 6% from the 45. And if we check the smaller reading, we should be getting somewhere around 5 microfarads. Usually if the capacitor is bad, the reading will be much lower than the rating. Next up, we have the diode test. This is used to check diodes, which are basically like one-way check valves in the electric world. These things allow current to easily flow through them one way, but prevent it from flowing the other way. The way the meter accomplishes checking diodes is by simply sending a small amount of voltage to one of the leads. And when you put both leads on either side of the diode, you'll have voltage going one way and not the other. So one way, you would get 6 volts, and if you swap the leads, you would get 0 volts. If the diode is bad, then you would get a read on both ends or get no read on both ends. Next up is temperature, and if your meter has the temperature option, usually you have to disconnect the meter leads before you can plug in your probes. After the leads are disconnected, I move this little knob to temperature, and then I can plug my probes in. Most meters are only going to have one of these plugins. This meter has 2 of them, which is perfect to measure the temperature difference between 2 points, also known as the delta T. You can use a K-type temperature probe or a clamp-on temperature probe. So right now I have T1 selected, which is the first temperature probe, this guy right here. If I grab it with my fingers, you can see the temperature is climbing up. And if I press select, that brings me to T2, which is my clamp probe. And if I press select one more time, now we're getting the difference between the 2. So if I grab this guy one more time to heat it up a little bit, The temperature difference between the two probes is about 6 degrees. Next up is amperage, and this is used to test how much current an electrical device or a motor is drawing. The easiest way to check the amp draw of something, whether it be a motor or some other electrical device, is to use the amp clamp. If we compare electricity to plumbing, the voltage would be equivalent to the water pressure, whereas the current, the amperage, is equivalent to the flow rate, the gallons per minute. So when you put your amp clamp around a wire that is powering some electrical device, you will see how much current is flowing through that wire. And it doesn't matter if you put your clamp on the neutral or the hot wire, both of them should give you the same read. One important thing to note is that the hot wire does need to be isolated from the neutral. If you put your clamp around both wires, the hot and the neutral are going to cancel each other out and you're not going to get any reading. You can also check millivolts with this meter by pressing the select button, and we see a little M up here. So if you're using your meter to check something that has really tiny voltages, like fractions of a volt, you can use this setting to accurately measure those voltages. Keep in mind that voltage and millivoltage are very different. A millivolt is only 1/1000th of a volt. And then we also have this setting. So we have amps right here, and then the backwards U stands for micro. So on this setting, you can check microamps. A microamp is only 1/1,000,000th of a regular amp, so you can't use the amp clamp. The reading is way too tiny for this thing to be able to pick it up, so you have to use your meter leads, and you have to set your meter in series with whatever it is that you're checking. In heating and air conditioning, microamps are often used to test flame sensors on a furnace. Next up, we have non-contact voltage, labeled as NCV. With your meter set to non-contact voltage, you could use the tip of the clamp as a voltage pen to detect if there's any power in the area. It's a fast and easy way to check if there's any power at an outlet, a light switch, or if a power cord is energized. Most meters will also have a hold button, which, when pressed, will freeze the reading on a screen just in case you want to take a picture of it or show it to somebody before it disappears. And a backlit display is another feature that most meters will have. And with this particular meter, there's also a little flashlight that lights up right on the tip of the meter, just in case you need a little extra light. Next up, we have the minimum, maximum, average, and peak button. If you select max, while you're measuring voltage, amperage, or resistance, whatever reading that the meter will register that is the highest, that one is the one that's going to stay on the display. Min is the same thing, except it records the lowest reading that the meter registers. And then we have average. If whatever it is that you're measuring is fluctuating, let's say you're measuring an outlet and the voltage is bouncing around from 115 to 122, the average would simply give you the average read, which would probably be around 117 volts. And then if I press and hold this button, we have peak max and peak minimum. When you select peak, it's the same thing as the regular minimum and maximum, except it's almost 3 times as sensitive, so it reacts a lot faster. For example, if you're measuring voltage and it spikes just for a fraction of a second, if you have it set to peak max, it'll still be able to catch that. Next up, we have inrush current, which can only be used when the meter is set to the amp setting. The inrush option would be used to check amperage when motors start up, because when a motor is starting, it draws a lot more amps than it usually does while it's running. So if you're measuring amperage and your meter is set to inrush, your meter is going to catch the highest spike in amperage right when that motor is starting up. This test is useful to see if a motor or compressor is drawing locked rotor amps. Next up, we have Hz, which measures frequency. And frequency is the rate at which current changes direction per second. In America, the frequency we use is 60 Hz, but in many other parts of the world, such as Australia, China, and Germany, they use 50 Hz. Frequency is only measured with alternating current, and an easy way to check it is to simply stick your meter leads into a power outlet and see what you get. You should have exactly 60 or something very close to it. And the last cycle I'm going to go over is the duty cycle, which is usually labeled as duty or a percent symbol. The duty cycle is used to determine the ratio of time a load or a circuit is on compared to the time that it is off. For example, if you have a welding machine that has a duty cycle of 25%, that means that machine can run at a designated amperage for 2.5 minutes, followed by 7.5 minutes of cooldown. Which means if you need to be welding continuously for a long time, 25% duty cycle is actually bad. You'd probably want something that is at least 50 or more. If you measure duty cycle on an outlet without anything plugged into it, you should be getting about 50%. Because alternating current, it goes back and forth, and if nothing's plugged in, it should be about 50-50 between negative and positive. And that is all I had. I hope you found this video useful. If you have any other multimeter questions that I left unanswered, please let me know in the comments. I'll see you there.